So we're going to build upon what we talked about on 7.1. So we talked about all the properties, the identities. We talked about the ratio property, reciprocal, quotient, Pythagorean, and all those formulas. I give you a whole page of them. So you're going to need them handy. And the goal, the homework, I think it's better to do this on paper. Just do every step, because that's how the exam's going to be. Because if you notice the homework, they're just kind of just filling in blanks. So it's not the same. This one kind of is the same, but as you can see, they look more complicated than they need to be. But in paper, it's a lot better. So let me show you. So big picture, you pick a side of the equal sign, and you want to make it turn into the other side. Rule of thumb is you want to pick the more complicated side, because if it's too simple, then it's really difficult to get to the other side. Okay. So let's do a bunch of these and start practicing using our identities and how to prove that one side is equal to the other side. That's essentially what we're doing. We're going to prove that this is equal to 1. Okay. Excuse me. Excuse me. All right. Let's start with number 3, I guess. All right. So 7.2. Verify trig identities. So it's essentially what we are doing. We're verifying, meaning we're proving that one side is equal to the other side. So the first one is pretty simple. At least I hope it is. We should know that these are reciprocals of each other, right? When you multiply reciprocals, they cancel and you're left with 1. So we can see that a little easier if we use the ratio, because tangent is equal to sine over cosine, cotangent is equal to cosine over sine. So that's the ratio. Now, if you multiply it, I mean, you can kind of see that these are going to cancel already, but if you didn't see it, you can multiply it together. And once they're on top of each other, they cancel, right? So sine's gone, cosine's gone. And when stuff cancels, you're left with a 1. So we've shown that, yeah, this side is equal to 1. So that's what we want to show. You see how these are done, right? We're just trying to get to the other side using any property we have written down from yesterday and previous classes. Okay. You may have to do algebra. You might have to add fractions, or you might have to use an identity. It depends. Okay, let's do another one. So 1 plus sine, 1 minus sine is equal to cosine squared. So you need to choose. So when you start these, you need to choose one side. You don't work on both sides. Okay. So as I said, pick the more complicated side, right? This looks harder to deal with. So let's start with this side. So that's why I want you to start your questions on the test. Just write down, excuse me, write down where you're going to start. Here I'm going to multiply it out. When you multiply everything, you're going to get this, right? Because difference of squares tells us it will always multiply this way. But 1 squared is the same, so who cares? Okay, so I need to get a cosine. So what property would I use to get to here? Because we're almost there. I know it was a few days ago, but you're saying the Pythagorean, you want to substitute sine, is that what you're saying? Raymond? Yeah, we could do that. Let's just try it out, see what happens. Right, we just want to try stuff. So if I'm going to do it in here, that becomes 1 minus cosine, right? But there's a minus in front. So we get 1 minus 1 plus cosine when you distribute. And you see these ones will cancel, leaving you with cosine. Now there's many ways to get there. Raymond suggested we try that identity, right? And it worked out. So that was Pythagorean. We call them properties? No. Identities. So we go. So we know that sine squared is equal to 1 minus cosine. And cosine squared is equal to 1 minus sine. So we could have used this one technically, right? Well, but if we use the other one, it's still going to work out either way. Any questions on number 2? Okay. I'll turn the page in just a moment. That's working fine, I guess. Also, don't worry about your exam grade until I go in there and grade your stuff. Right? There's still a lot of, like I said, I don't really care what answer choices you make. I need to grade the work. So it might be much higher than whatever you got. Okay. assuming you turned in quality work. Yeah, you guys cool on page 1? Let me know if you need me to turn the page or turn it back. Okay, so instruction is going to be the same. Just verify the identity or prove or whatever. Just start on one side, get to the other side. Here they use beta. Doesn't matter though. So instead of theta or x, it's cosine squared beta, sine squared beta, cosine squared beta. Okay. So if you're doing this on your own, what side would you choose to start on? What looks more complex? It's a 3, by the way. Most of the time, there's one side that's better than the other. Sometimes it's equal, but it's kind of rare. Yeah, I think the left side is better because it has 2 trig functions where this one only has 1 and a constant. Like, I don't know how to deal with that 3, honestly. But I see something that I see a cosine squared and a sine squared. So we can use Pythagorean on that probably. So I say we start on the left. We just want to try something and see what path that takes us on. See what happens. All right, so I'm trying to get to cosine, right? So this side is technically a hint, what we could try. This is already a cosine, so that's good. But this is a sine squared. So there should be a hint here telling, well, maybe I should change this guy into a cosine, see what happens, right? Because we know that Pythagorean says we can change this to 1 minus cosine squared beta. Okay. We know that sine squared beta is equal to 1 minus cosine squared beta. Okay, so all these are equal. All right, so I just substituted sine squared here, distribute the 3. Now I'm there. It looks like we might be done, right? 3 cosine squared plus 3 cosine squared. 3 plus 3 is 6. And then minus 3 is just there. And that's where we want it to go. Any questions on that? Do you see the logic? And don't forget, there's not just one way to get there, right? You can try all kinds of things. But there's usually a short path that you want to take, but it doesn't always happen. Sometimes you take a long path, but still works out. Okay, here's the next one. Assuming you guys are cool on number 3. All right. So number 4, which side do you think would be best to start with? Yeah, the left side looks kind of annoying, right? So maybe we should start there. So that's usually what I go with. I'm like, okay, does it look like a pain? I guess I should probably start there. Is it more complicated? Most of the time when you see fractions, you want to go with that side. Okay, if there's no fractions, then you want to start with something that could be turned into fractions. Although, I feel like this one might be almost equal, right or left, but my instincts say start with the left because I see weirdo fractions. So just write down the side you want to start with and then begin trying to figure out some sort of identities. Okay. So right now you should notice that there's a tangent and a cotangent in the bottom, right? So if we look at our formula stuff, here, the quotient identities or reciprocal. I think I call them reciprocals in your notes. I don't have that note up right now, but here's the PDF. This will work for us. We know that 1 over tangent is the same as cotangent, right? So we also said 1 over cotangent is tangent. I should have put that here. Oh, well. The notes, the formulas I gave you are more complete. So let's just use that, I guess. I'm hoping you still have them. Sorry, hold on, I forgot to switch. Okay. All right, so this is what I'm thinking. As soon as I see this tangent on the bottom, I'm figuring, you know what, those are reciprocals. That 2 is just in the way, who cares? You agree that this is the same as the previous line, right? If I put the 2 in front, it's just going to be 1 over cotangent, 1 over tan. Same thing, right? So at this point, we just need those formulas that says tangent x is equal to 1 over cotangent, and cotangent is equal to 1 over tan. I believe that was reciprocals in our notes. So right here, change it to 2 cotangent plus 2 tangent. reciprocal identity. That's what these were. At that point, you see where we are, where we wanted to go. We show that the original is equal to 2 tan plus 2 cotan. Any questions on any of those steps? Does that make sense? Inverse. I don't think there'll be any identities that will require inverses. They could exist. You could have identity types that incorporate inverses, but you're not going to see that. So you're just using algebra and factoring, just basic algebra and your identities from the formula sheet or the notes that have been given you over time. That's all you're going to need. Then go ahead and give you all the reciprocals just in case you don't have them. Sine. I'm pretty sure you have these somewhere, but here we go again. Who cares? All right, so those are all the reciprocals. Then any other questions on example 4? Okay. I don't know if you need me to turn the page back. You see how we're not solving for anything, right? We're just proving a statement. We're showing quality. That's all we're doing. And the purpose of doing these types of problems is to basically get you comfortable with the manipulation of all those identities, because you can, as you can see, you can change them quite a bit to solve all kinds of actual problems. But right now we're just practicing. So there's all these formulas, but you may not be comfortable using them yet. Okay, so number 5, obviously the left looks disturbing, so we should start there. The right side is just a secant or 2 secant. I have no idea how I would change this into these two things. I think that would require like out of the box fancy algebra kind of stuff. But over here, there's more things to do, so it should be easier to get to 2 secant. Okay. And the rule of thumb is if you see fractions, add them, see what happens. So we have an LCD of cosine times 1 plus sine, right? So I'm going to start with the left. All right, so the LCD is right here. So I'm going to need this on the bottom of both fractions. So this needs 1 plus sine. This needs cosine. So introduce it, multiply the top and bottom. Oops, wrote that weird. And then this guy, multiplied by the cosine that it needs. I'm not going to go ahead and multiply just yet. Oh man, next stuff. So I'm just going to leave it like this. 1 plus sine, 1 plus sine. Over cosine times 1 plus sine. Now I might as well just change this to cosine squared. LCD, I'm going to keep it looking the same. Okay. All right, so you guys still with me, right? All we did was introduce LCD and got ready to add the fractions. One plus sine times 1 plus sine. 1 plus sine squared. Add the numerators. Denominators will stay the same because we have the LCD. There we go. All right. At this point, we should probably multiply this out. See what we can do. So FOIL that out, that'd be a 1 plus 2 sine plus sine squared plus cosine squared. Okay, so here we are. So all I have done is added 2 fractions. Haven't used any identities yet. So now that we've added them, what identity would you use? Or do you see something that you can do here? Yeah, we see squares, right? So that should be a hint that Pythagorean could be handy. What is sine squared plus cosine squared? That's the very first Pythagorean. You guys remember? Yeah, that's going to be 1. So this right here will combine into a 1. So on the next line, we'll just simply have 1 plus 2 sine plus 1. So Pythagorean sine squared theta plus cosine squared theta is equal to 1. The variable doesn't matter. It's just always going to be, it's going to be the same. Beta, alpha, theta, x, who cares? Okay. So at this point, you should see you have 1 plus 1, right? So we got 2 plus 2 sine over cosine theta times 1 plus sine theta. So I want to finish in the next page. So let me let you catch up. I'm going to get a drink really quick. 1 minute. Give me a second. Okay, sorry. You guys cool on that page? Any questions on any of these steps before I turn the page? I'm going to rewrite this step and go from there. All right. Cosine, right? Yeah. Okay, this is where we left off on the last page. So I'm going to factor 2 on top because I can see something can cancel, right? Now that it's factored, you can cancel something. We couldn't cancel until this moment. These are gone. So factor 2, then cancel the like term. That's all we did there. So at this point, we have 2 over cosine. So we should see that the finish line is pretty close. this is technically 1 over cosine times 2. So that should be your biggest hint that this is secant. This is where we wanted to go. We're using the reciprocal identity. Any questions on number 5? Okay. So I did a bunch of them from your homework. They should be similar, but still practice doing all the steps, because I think the homework might try to walk you through it a little more. But you need to be able to just start somewhere, try stuff, get to the other side. But that's all for 7-2. 7-3, we're actually solving things, so it's different. Okay. Any questions on 7-2? Okay. Looks like the same thing. Let me open up 7-3 then. Okay. You guys take a short break. Then we'll hit 7-3 and maybe 7-4. All right, so it's 12:30, sorry. We'll start back up at 12:40. Just take a short break here. Forgot to unpause recording. Oh, well, okay. Missed that first example. So rehash this. Add the cosine over, subtract the 2 over, divide by 4. Apply cosine inverse on both sides. Calculator gives us 120, which is the same as 2 pi thirds either converting it yourself or looking at the circle, because this is an easy angle. It will be on the circle. To find the angle for the second set of, as part of the set, just take 360 minus what you found to get the other one. Change that to radians because the homework is using radians right now. So this is where we are, example 2. Now, since they did not say 1 period, we have to add that piece. So the actual solution will be they actually used x. So look at this. I started with an x and I switched to theta. So what I'm going to do is just go ahead and change it to theta. Less erasing. Okay. Understand that the homework had an x, and that doesn't really matter at all. You can write the solution as a set, and that's what they do. That's how this is how you have to plug it into the or type it in. Put your first piece plus 2 pi. So that's our 360, right? 2 pi n, comma 4 pi thirds plus 360, right? Times n. So there is my solution to this equation. Is there any questions about this? No, it's just the brackets symbolize a set. Like on paper, you should write it that way. In the actual computer thing, they're writing it like this. Let me show you. You just type it in, comma, whatever. So just type in the box. So they already have the x equals. You just type in the answer. I prefer putting this part first and then plus 2 pi n. It doesn't matter though. It should accept it. They put 2 pi n first. I just think it's weird. It doesn't matter though. Any other questions about example 2? Okay. Sorry, I'm spacing out. All right, example 2, move on. Okay, oh, it's still blurry, but all right. Well, this next one looks interesting, actually. It's problem 8. Example 3. Problem 8. try to stick with X this time, see how that works. All right, so same idea. Isolate the cosine, use inverse functions, and then find the pair to your solution. This one might be a little different. So I'm gonna add the 1 over. Don't write the theta, man. X. X. So plus 1, both sides. Divide by 4. Let's get some minor steps here. Let me know if you want to see more steps. At this point, we got to square root both sides. And when you square root both sides, you have to tack on the plus or minus. And remember that you can separate the square root like this and get square root of 1, which is 1, square root of 4, which is 2. So we get cosine x equal to plus or minus 1/2. I showed the square root steps there just in case you forgot. But notice we have a plus and a minus. That's really 2 equations we have to deal with. So we're gonna have a lot more answers. So deal with the half and then deal with the negative half. Okay, so cosine inverse of both sides for both of them. Right, cosines cancel, leaving you with the whatever argument you have here. Okay. You use your calculator if you like. We did the negative half earlier, so cool. It's right there. 60. Technically, we should already know that, but who cares? So 60 degrees. I'm going to change it to radians in a little bit, but it's a little easier to see right now with degrees. Okay. So both of these are going to have a set to that, a pair, I guess. Okay. So this is the first one. So the second one will be 360 minus 60, right? Which is 300. So that's the first, second. We'll say this is the third. So the fourth will be 360 minus 120, which gives us the 240. So we have a few 60 degrees plus, well, let's go ahead and change to radians actually. To look at your circle, let me find it. Okay. All right, so here we go. 60 degrees is pi thirds. I'm gonna write that down real quick. Pi over 3. 300 is 5 pi thirds. Okay, cool. You can always convert it yourself, but since these are the easy angles, known angles, I guess I should say, I'm just gonna look at the circle and save time. 120 is 2 pi thirds, which we already knew that. 240, we did that earlier, 4 5/3. Okay. Now, do you guys notice a pattern? So I'm going to circle all the solutions that we got. This one, this one, this one, this one. What's the distance from 60 degrees all the way to 240? Yeah, it's 180, right? So do you see that if I would have said one solution is pi thirds, or sorry, 60 degrees plus 180, I would hit this one and then this one, and I hit another 180. I keep going back and forth over and over again. So instead of doing 4 answers and saying 6 degrees plus 360, 120 plus 360, 300 plus 360, 240 plus 360, instead of having 4 sets of solutions, you can kind of just merge them into 1 or 2, because it's, you can just keep hitting the same spots. Does that make sense? Because I technically could say this, right? Let me just, what we did earlier. Technically, I could have said, yeah, we got this answer, cool. And then I have this one. I know I need to change to radians, but it's a little easier to understand right now, like this. Right? Do you agree that I can do that technically? But as you saw, that I could break these two into one, or merge them together. Because 60 to 240, we said was 180 degrees, right? So I could also say, you know what, it's just 60 plus 180 degrees times n. So this and this would be this one. And this is the distance of 180. So I could just say 120 plus 180 degrees. So I can just merge 2 sets together. Since I'm hitting those 4 corners, instead of representing each one separately, I can represent 2 of them at a time. Does that idea make sense? Although theirs is in radians. So like on an exam, of course, I would accept this first one. I mean, I think this makes more sense, but you should be able to see that I can combine these together. right? The homework seems to combine them. See, this is the one we just did. Number 8. So their answer was just pi thirds plus pi n, which is what we had. 2 pi thirds plus pi n. But you can't really see how they got there without finding all 4 spots yourself and then merging them together. Is there any questions on this idea? Or any steps on the question here? Okay, so remember, example 3 makes sense. Okay. Let me find another one. All right. So they're not always going to be just a single sine or a single cosine. Sometimes you have to factor and you'll have multiple trig functions. Let's do a different type. Okay. Example 4. Problem 9. Yeah, I think it's 9. Let me check. Yeah. Cosine cubed x minus cosine x equals to 0. So if you can't isolate a single sine or cosine or tangent, whatever, you have to try factoring or try identities. That's all you can do. So right now you should see that cosine is in common with the top, with the left side here, leaving me to here. And you should also know whenever you have something factored and equal to 0, then you can set each piece equal to 0, each factor. Something we learned way back when. So now we can solve the problem separately. Okay, so this is no big deal, right? Screw both sides and you're gonna get, I'll go ahead and show it. Okay. So now let's find out when is cosine equal to 0. When is cosine equal to 1 and -1? So this is technically another 2 pieces. Okay. Okay. So we can use our inverse functions, arc cosine or whatever. Both sides. So that'll give me x equal to 90 degrees. Let's see. Oops. Yeah. And then we said to get the other one, right? That's the first one. Do 360 minus 90, 270. So the other one will be 360 minus 90, which is 270 degrees. So there's my 2 answers. Where is cosine 1? Well, there's only one place. This one is, it's going to be 0. This one's going to be pi. They're not going to have 2 sets, actually. If you look at your circle, it's not going to happen. Okay, so there's only one x value that is 1 there. There is not 1 anywhere else. Over here is -1. So we're only going to have one answer for cosine equal to 1, which is right here. And cosine equal to -1 would be right there. That's why I got those answers here. Forgot I'm using degrees, so let me switch back. Okay. All right, so got 3 of them. Let me look at the homework again. They did not say 1 period. So technically, I should be adding for each piece 0 degrees plus 360n, 180 degrees plus 360n, 270 degrees plus 360n. But we can merge them together. Let's look at your circle. So our 3 solutions, where's that pen marker thing? Is here. Here. And here. Oops, 0 degrees. So if you're going to try to collapse some of those together, we can combine 0 degrees and 180, right? Because 0 plus pi n would be this guy and this guy. So I don't need to separate these 2. This one I'll just separate, leave it by itself. So I think what I'm going to do is have one solution that says 0 degrees plus 180 degrees N. And then the 270 will still be a 360 N. So I can jump from here to there with a 180, jump back with another 180, jump back again. So every 180, I'll just keep hitting those these spots. That makes sense. If we use 90, if we would have had this answer, actually, yeah, you're right. I didn't think about that. Cosine is 0. Oh no, hold on. Yeah, we had a 90 degree, right? The first thing we wrote. So that means we can collapse them all 4 into 1. So from here to here is 90, to here is 90, 90, 90. So every 90 degrees, I will hit a solution as long as I start here. So let's get back to the paper. So I should have had 90 degrees plus 360 plus 360. Okay. So we can combine all this into a simple 0 degrees plus 90 degrees N. Or 0 degrees plus pi over 2 N. That should work. Let's look at our answer. Yeah, here it is. So they got just pi over 2N. Anyway, you see how they're condensing the problems. Is this making sense? Let's do one more and then we're moving on to something else. Or maybe we'll see how it goes. Tomorrow is Tuesday. Do that guy. Yeah, let's do one more. Time for some homework and questions about whatever. Okay. So you had a type that was, we had to factor. Oh, the first one was just trying to isolate sine or cosine. And then you had somewhere you had to factor common, like a GCF. Now here is a quadratic type, problem 11. So there's 2 cosine squared x plus cosine x minus 1 equals to 0. So this should look familiar. It looks like a quadratic equation, right? And to make it more obvious, you can do a substitution, like w equal cosine. So 2w squared plus w minus 1. Factor, right? If you do your trial and error or AC method, I don't really care what you use, you'll end up here. And we should know that once it's factored, you set each piece to 0, like we did earlier. But w is made up, so bring back cosine. It's a dummy variable in order to factor. Any questions on the substitution or the factoring here? This okay? I skipped the factoring step. Okay, so this is a quadratic type. But this, once it's factored and ready to go, it's going to be similar to what we had earlier. So add the 1 over, divide by 2, you get 1/2. Subtract the 1 over, you get -1. Okay, so then you find the angle where -1 happens, which is pi, right? And then the 2, we've done this one quite a few times already, so I'm just going to skip to the end here. We will get, the first solution will be 180 degrees plus 360 n. Second solution will be pi over 3, 1/2 would be for cosine 60 degrees. And then the last one will be 300 plus 360 n. Of course, they want it in radians, so that'll be pi plus 2 pi n pi over 3 plus 2 pi n 5 pi thirds plus 2 pi n. Let's see if they broke it down any further. Nope, it's just like that. Any questions on example 5? Okay, so we'll stop lecture here. I guess let's spend some time, let's take a small break, and then if you have any questions about your exams or your homework, let me know, and then we can work together. If not, please work on your homework for the remainder of the time. I'll be back in about 10 minutes.